Okay, so we just calculated the change in enthalpy for the combustion of methane, and we found just based on looking at the bonds that were being broken and the bonds that were being formed, we would predict that there should be a change of minus 824 kilojoules per mole of methane. So, I went to the internet. I look at the Wikipedia page on methane, and when I scroll down, we've got all kinds of cool data.
Oh, it's colorless gas.
It's a colorless gas. It's odorless. What?
But it smells. Wait, does it kill you? Wait, what the? Something just flashed.
Did you smell something when you
They
open
put
this
the
up?
rotten egg smell in there.
Yes, they put something in there so that it doesn't fill your whole house with odorless gas.
But what if you want to
leave your
die?
stove on, and then you light a match to light up your cigarette, and you,
Why can't they make it smell like something good, like cinnamon?
or you light your pilot light.
No, that's
your
the
furnace goes off.
the gas.
All right, as we scroll down here, oh,
Why can't they just make it smell like nothing?
this says that the standard enthalpy of combustion should be minus 891.
Oh, Lord.
So we got pretty darn close. Pretty darn close.
Pretty close.
Just using average bond energies, right? And not factoring in anything else. Just looking at the bonds broken and the bonds formed, we got pretty darn close to this amount of energy.
What kind of percent you're
But there are many ways of calculating or estimating the change in energy for a chemical reaction. So I alluded to the fact that really it doesn't matter what process we use to get us from our reactants to products, as long as we get from our reactants to our products by some processes. If I know the change that occurs in those processes, it should give me the change for the reaction. So this is one way of doing it. One way of doing it is to think about what is the potential energy change if we were to take these molecules, completely break them apart into their individual atoms, and then allow those individual atoms to recombine into our products. But another pathway that we could take, and one that is a little bit more useful experimentally, here my potential energy 0 is what? What's 0 represent on this graph?
potential energy 0?
Physically, about this reaction. What does 0 on that graph represent?
There's no attraction. Yeah, they're all individual.
They're all individual atoms,
Oh,
right? But we don't have to use that as our 0. When we measure, if I want to measure how much height changes from this room to outside, what can I do?
I mean, you can make outside the base.
I could make outside 0. I could figure out how high up above 0 we are right now, and then compare that to the 0 that's outside, and that would give us our change, right? I could use my phone to do it. How does my phone do that?
Altimeter.
My phone can actually, with GPS, tell me how high I am at different points. So I can take a GPS measurement in the room. I can take a GPS measurement out of the room. Okay. But the GPS is not measuring how high I am above some certain 0 point. What is it actually measuring?
How high you are.
It's actually measuring how far I am below those satellites. Right? It's measuring it, it's doing a timing thing, how long it's taking those signals from those satellites to reach my phone. That's how it's calculating how far I am away from those satellites. Now it does another thing, because since it knows how high those satellites are above sea level, it's sort of doing some work to say, okay, well, you're really this far above sea level. Okay, but in reality, it's like I'm saying, okay, here's my satellites. Mr. Bull's third floor is here. Outside is here. So if I know the change from third floor to the satellite and the change from the satellite to outside, then I can just subtract those two and that will give me the difference in height. Okay? I could also set as 0 the center of the earth. And I can figure out how far third floor is from the center of the earth. I can figure out how far outside is from the center of the earth. And just compare those numbers. It should give me the exact same answer, right?
Ooh. What if you make 0 just the second floor?
If I make 0 the second floor, it should not matter what process I take, whether I go up to outer space and back, whether I go to the center of the earth and back, whether I go to the second floor and then down to the outside. If I know how much each of those changes, because each of those is getting me from the same start to the same end, they should give me the overall same change. Does that make sense? Okay. So the second method we're going to use to calculate the change in enthalpy for a reaction is we're going to set as our 0, not a bunch of atoms all broken apart in individual atoms, but we're going to set as our 0 the elements as they naturally exist. So I'm going to label this elemental states. So for this example of burning methane, what are the elements that we have?
Carbon.
Carbon. How do we normally find carbon?
Carbon dioxide.
Solid, liquid, gas?
Oh, gas.
Diatomic, monoatomic?
Oh, food.
Diatomic gas.
Nope.
No, wait.
Just carbon solid, like coal.
Oh,
Diamonds.
Diamonds. Graphite.
yeah, the natural state.
Actually,
I mean, diamonds are pretty
graphite
common.
is sort of the 0 state. Okay?
How-
What other elements do we have in there?
Oxygen.
We have hydrogen. What? How do we normally find hydrogen?
Gas.
A diatomic gas.
We don't find it.
H2. Right? You gotta remember Honkelbrick.
Brinklehopper.
Rinkelhoff.
Not Hopper.
Hoberwinkel. Von Brinkel. You gotta remember what elements are diatomic. We also have oxygen in here. Oxygen is also a diatomic gas. Okay? So what we can do conceptually is say, why don't we gather all the elements that are involved in this reaction? Let's take those elements and turn them into our reactants. How much energy would it take to form methane from its elements? Well, what I have to do is I'd have to take carbon solid and 2 hydrogen gases and react them. Whoops, this is a diatomic gas. And react them and form 1 mole of CH4.
Wait, what is the bar in reference to the equation?
What is the what?
The bar, the line in reference to the equation.
It's going to be a change from my elemental states to my reactants. So we're going to have to figure out what that change is to see whether it's actually positive or negative. Close, yes. Okay. This P. Take her, get rid of her, we don't want her. So like Pendravinsky.
Yeah. How do you pronounce Pendavinsky?
Okay, so if I take that carbon and that hydrogen and make methane, that reaction is going to have some change in energy. I might rewrite that because you probably can't see it very well, right? I gotta get new markers. These are all starting to get.
For your birthday.
If you're thinking about any last minute gifts,
I won't be here tomorrow.
You thought I was thinking about it.
I won't be here on Friday.
Ah, so you're gonna be working off the birthday celebration.
So-
he's gonna be hungover.
This is a reaction that we could do in the lab.
Whiskey stones.
Yeah.
You're gonna be sucking on those whiskey stones.
Yeah. This reaction has an associated change in enthalpy. And because this is a special type of reaction, where we are forming a substance from its elements, we call this a delta H formation. Okay? Now, one other thing we put in there we put a little circle up here to say we want to carry out this reaction at standard conditions. We want to do all these different changes at the same conditions, otherwise we could get different numbers. Okay? So I can actually look that value up. It's on the Wikipedia page for CH4. Right above. The standard enthalpy of formation of methane is negative 74.84 kilojoules per mole.
87.
I can't read. So to take those elements and turn them into methane actually releases 74.87 kilojoules per mole of methane that I'm going to make. Okay? Now, what's my other reactant? O2. How much energy does it take to form O2?
None.
Hmm?
It's already an element.
It's already in its elemental state, right?
Yeah.
So we can essentially say, well, if we gather up all these elements, to make our reactants would actually release a total of 74.87 kilojoules. Right? Because we have to make our CH4, but we don't have to make our O2. It's already in its elemental state. So this line's pretty long. In reality, we have just a slight difference from the elemental state to our reactants of negative 74.87 kilojoules. All right. Now we have to look up values for our products. We have to say, okay, well, if we were to take those elements and form our products, what would the change be there? If that change is greater than this change, we're going to have an exothermic reaction. If that change is less, we're going to have an endothermic reaction. Right? Now I know burning methane is exothermic, which is why I drew that one lower. Okay, but let's look up the values. Where are we going to look them up? Well, I could search up a table of standard enthalpies of formation. There's lots and lots and lots of tables. Cool. There's Appendix C, wherever that one is. Oh, wait. We have CO2 on here. Okay, you probably can't read that very well. We could also, we don't have to look there. We don't even have to use the interwebs.
We can just ask you.
We can refer to the Bible.
No.
70th edition.
Yes, this is just the 70th edition from 1990, but I don't believe there's been any major advancements in measuring the enthalpy of formation of any of these things.
More sig figs.
Probably. Okay, so we can look somewhere in this big nasty booger here. Table of isotopes, no, we don't want that. Gravimetric factors, whatever those are. Physical constants, probably not any of those.
Is there not?
Did you ever read that book from like front to back?
It's not that kind of book.
Oh,
I mean, if you really want to read through a whole table of sound velocities of water at 212 Fahrenheit, you could read this whole page, but that's...
Not like
Nope.
that guy who said it.
This is reference. This is just when we want to look up values. Selected values of chemical thermodynamic properties. Yeah!
There's there.
Yeah, CO2's there. What about H2O?
It's probably on the internet. If you scroll down.
Yeah, scroll down.
No, it actually ends. These are all just the carbon ones.
Wait, we were CO2? Which one?
Looking for H2O. That's our other product.
H2O.
Search it up on the web. It's probably there.
Page 2.
Like a video.
What we got here?
What if we made a child memorize all these values?
That child.
Logan, get memorizing.
Oh,
He's taking
Okay.
an AP test next year. Come on, get him
This
on.
one's got some good values on it. All right, now, don't worry about this delta G or this S. We're going to worry about those later. We're just worried about delta H of formation. So CO2, same thing on this table. It's saying that to form CO2 from its elements releases 393.5 kilojoules. Okay, so again, taking carbon, but now taking oxygen and forming CO2, this has a change in energy, and we call it delta H of formation because it's forming CO2 of negative 393.5 kilojoules per mole. When we look up water, that's going to be H2 plus O2 forming H2O, right? How do I balance it?
2 and then 2.
Wrong.
2, 1, 2.
Wrong. We have to use a half.
What?
Because, by definition, a formation reaction is the change in enthalpy associated with forming 1 mole. So when we balance a formation reaction, it has to have a 1 in front of the product. Okay? Now, when I scroll down here, I'm going to pull the screen down because we've got a lot going on. When I go down to H2O, uh-oh. It is very important to know what state your substances are in. Why?
Because that changes how much energy.
We just learned in the other unit that there's a change in energy associated with changing the phase, right?
Yes.
If we look at the difference between these two, liquid and gas, what's the difference?
44.
It's about 40, what? Kilojoules per mole. That number sounds familiar.
That's the steam.
It's a fusion.
The enthalpy of vaporization.
That's the enthalpy of vaporization of water, right? To turn liquid water into gaseous water takes 40.7 kilojoules. But wait, this is 44. That's because the enthalpy of vaporization is being measured at 100 Celsius. What are these being measured at? Standard conditions, not STP, standard conditions. What are standard conditions?
1 atmosphere, 25 degrees Celsius.
1 atmosphere and 25 Celsius. So room temperature, room pressure. 298 Kelvin and 1 atmosphere. STP, remember, is for gases. Remember the nastiness that we had to do when we subtracted the vapor pressure of water? No, because you guys don't remember when we did the molar mass of butane lab. When we did the molar mass of butane lab, we assumed the pressure in the tube was the same as the pressure in the room, but there were 2 gases in the tube. The butane we bubbled in and also the water vapor that was evaporating because we were doing it in the presence of water. If we'd have done that experiment at 0 Celsius, the vapor pressure of water would be very close to 0. That's why they do standard temperature and pressure for gas collection things is at 0 Celsius because it minimizes the vapor pressure of water. Okay, so if we actually burn methane, we're going to make it rain.
I'm making
It's going to come out as a gas, right? So let's use H2O gas, negative 242. Okay, now, here's the other thing you have to keep in mind. The reason I was very strongly stressing how to write these equations is that this is the energy change associated with forming 1 mole of H2O. But in the reaction, we actually form 2 moles of H2O. So yeah, this times 2. So we can think about like, okay, here's one of the CO2s. We are going to get out negative 393.5 kilojoules. I'm going to make one of the H2Os and get out 242 kilojoules. I'll make the other H2O and get out another 242 kilojoules. Does that make sense? No? Okay. Now, conceptually, again, sign is very important. What we really want to do is we want to know the change from here to here. Right? but both the changes we calculated are actually from here to here, right? Which one of those sets of arrows is drawn in the correct direction in terms of what's actually happening in this reaction? The red one, right? Because we are actually forming our products. So really, we have to take this number, we have to reverse it. Because we're not actually forming our reactants. Conceptually, we could think of this as taking our reactants, how much energy would it take to turn them back into their elemental states, and then allow those elemental states to turn into our products. Okay, so I'm actually going to reverse the arrow here. And so really this reaction requires us to put in positive 74.87 kilojoules, and then we release 393, then 242, then 242. So if I add up all those changes, it'll give me the actual change for the reaction. So this is where we get that third equation on your equation sheet. Another way of calculating the delta H for a reaction is to add up all the delta H of formations at standard conditions. Well, there's a subtraction in here. So the question is, are we subtracting reactants minus products or products minus reactants? Which one did I have to flip the arrow on? Reactants. This is actually reactants, and this is my products. Okay? Because we are actually forming our products, but we're not forming our reactants, right? We're breaking apart our reactants back into their elemental states. So it's going to be the same magnitude of energy change, but opposite sign. Okay? Whereas conceptually for the bond energy thing, we were actually breaking the bonds in our reactants, right? So in that case, the positive one had to go with the reactants. So that's why it was change in bond energy for the reactants minus the change in bond energy for the products. Because in that conceptual thing, we weren't breaking apart our products into individual atoms. We were turning the atoms into our products. So that's why we had to reverse the sign on the products one. Here we have to reverse the sign on the reactants one. Because we're not forming our reactants from their elemental states. We are forming our products from their elemental states. Okay? So for this reaction, we could say, let's take 1 times the delta H of formation of CO2 plus 2 times the delta H of formation of H2O. And subtract from that the delta H of formation of CH4, one of those, plus 2 times the delta H of formation of O2. That's what the equation would look like. Now you also have to be very careful. Some tables are going to give you this. The one I just brought up, it does. Guess what number it has next to O2? For delta H of formation. What number is going to be next to O2 on my table? 0. It's already in its elemental state. Some tables won't give it to you. On an exam, they might not give you this. They would expect you to know that the delta H of formation of something that's already in its elemental state is 0. It doesn't take any energy to form O2 from O2. It's already O2. So that change in enthalpy would be 0. Okay? The rest of them, you look up in your table, which is essentially what we did here. So we get negative 393.5 plus 2 times negative 242. We subtract 1 times negative 74.87. Okay, these numbers out in front are the coefficients, right? These are how many moles of each of these things I'm forming or using. Okay, all right? plug it in. What do we get?
Negative 102.63.
Actually farther from the value that Wikipedia had than when we did it with the bond energies. Okay, but this is one way of estimating the energy change for this reaction using enthalpies as formation. Okay, I would assume most of you have probably done this before. So this will be reviewed. There's a third way. The third way.
Look it up.
There's a fourth way.
The third way is actually closely related to what I was trying to explain with the satellite analogy. The satellite analogy, I was trying to make the point that it doesn't matter by what way we get from point A to point B. All that matters is what is my overall change from point A to point B. Okay? So if I want to know what is the difference between the floor and the top of this desk, if I could see what is the difference between the floor and this desk, get out of that chair. And then what is the difference between this desk and this chair? And then, what is...
Make the jump. Do it.
What is the difference between that chair and this table? If I add up all those individual changes,
Oh, captain by captain.
It's dead post.
if I add up all those individual changes, if it gets me from the same starting point to the same ending point, the sum of those changes should be the same as the change in one step.
You could have killed us all. What if the floor collapsed?
Hess's law. That's what Hess's law says. It says that for a change like this, the path that we go through doesn't matter. All that matters is that we know where we start and we know where we end. So we talked about actually two different paths for calculating these change in enthalpies. One is to go up to their elemental states and see what those individual changes are, and then add them together to get the change in the reaction. The other process was to go all the way up to breaking apart all the atoms into all the molecules into individual atoms, see what that change is, see what the change is to allow all those atoms to turn back into our products. That overall change should be the same as this other alternate path, which it was. It was pretty close. 802 versus 824. We talked about why they're slightly different, okay? But turns out I can take any path as long as it gets me from CH4 and O2 to CO2 and H2O. I can go through 100 steps. And when I add them together, it should give me the same overall change.
Energy is conserved.
Well, this is what they're talking about in, let's see, 5C2. So in A and B, they talk about bond breaking like we just did. They talk about where we are compared to the beginning and the end, exothermic reactions versus endothermic reactions. F is really where Hess's law is explained. So we'll just read F. This
Although the concept of state functions is not required for the course, students should understand that use Hess's law ideas. When a reaction is reversed, the sign of the enthalpy of the reaction is changed. When two or more reactions are summed to obtain an overall reaction, the enthalpies of the reaction are summed to obtain the net enthalpy of the reaction.
Okay, well, we already used the first one. We said, well, if we're not actually going in this direction, if we're not actually forming CH4 from its elements, but we're taking CH4 and turning it back into its elements, we can just reverse the sign, right? That's sort of what we did, okay? The second part is to say that if we have multiple steps that we go through, we can add the change for 2 or more reactions to obtain the overall change for the thing we're looking for, okay? But in Hess's law, we're actually going to see we could undergo some process like this. Maybe we take CH4, we combine it with O2, and we produce carbon monoxide and an H2O and an H2. Maybe that's a reaction we can actually do in the lab and measure, okay? Well, that's going to have some associated change in enthalpy. But it doesn't get us to the point that we actually need to get, right? We formed our CO2 in one of our H2Os, but we've got this H2 in here, okay? So we might need to do another reaction. We might need to take that H2 and react it with an O2 and form an H2O and an O. But actually that doesn't get us to where we need to be because we've got an O in here left over and we formed CO instead of CO2. So maybe our last step is to take that CO and that last remaining O, turn it into CO2, and maybe that gets us back up to our original point. Okay? So each one of these steps is going to have an associated change in enthalpy, but because the overall sum of all these steps gets us from where we started, or where we wanted to start here, our reactants, to where we wanted to end, our products, if we add all these steps together, that should give us the change for that reaction. That's normally referred to as Hess's law. Okay? If I look up these values, or if I do these reactions and measure each one of these, I can sum the individual enthalpies of each of these reactions together, and it should give me the same overall change in enthalpy as in the other processes we saw. Okay? Question?
I have a question where, like, when you're calculating all these energy stuff, like, how does that put on the AT test? Because it seems like a lot of stuff that you need, that they require to give you in order to figure out.
Yeah,
Yeah,
wouldn't
they give you a table.
Yeah.
They give you the whole table.
In the next problem set, you're going to see an example where they gave a data table. They normally don't give super complicated reactions.
Sometimes it's a $10,000 shop.
But they could. I mean, this is not that complicated of a reaction. You should be able to draw Lewis structures for those things, right? So
Gotta do
it's not
lipids.
completely outside of the realm of possibilities. But yeah, in the problem set that I'm going to give you probably on Friday to get started on, you'll see you're actually going to do some of those, and there's a data table of bond energies right on there, or a data table of delta H of formation values. I mean, there's really only 3 you have to be given, so it's not too bad. All right, we'll do some Hess's law problems tomorrow. Solid, isn't it?
Wait,
Oh, I got you, my man.
when I took corrections, oh.